Alright, let's go. Number 10. The vacuum battery. Robert Forward, an engineer at Hughes Research Laboratories, was chasing a problem that had nothing to do with philosophy. He was hunting for exotic power sources that might one day drive spacecraft further than chemical fuel could take them. Standard physics said the vacuum's energy was real, but useless. A fixed baseline you could measure indirectly, never touch, never spend, like a bank balance you can see but can't withdraw. Then Forward's calculations showed something else. A cascade of charged, foliated conductor plates could, in principle, ratchet the Casimir attraction between them into a mechanical process, drawing the vacuum's own ground state down step by step and converting that drop into usable work. He published it in 1984 in Physical Review B under the title Extracting Electrical Energy from the Vacuum by Cohesion of Charged Foliated Conductors. A serious paper in a serious journal proposing what he called a vacuum fluctuation battery. Engineers pointed out the obvious catch first. The energy extracted seemed to match the energy spent arranging the plates. No free lunch. DARPA funded feasibility studies through the 2000s, including work by Garrett Model at the University of Colorado. Found the efficiencies too small to matter at any practical scale. Others argued the whole premise misunderstands the Casimir force as a fuel source rather than a boundary condition. The disagreement was never resolved. If the underlying physics holds even in principle, it means the empty air in your room contains an extractable energy density that dwarfs the fusion happening inside stars. Locked behind an engineering wall nobody is broken. If we ever do break it, what happens to a vacuum state we've been quietly draining for decades? No one has proposed extracting the next kind of nothing, because no one's figured out how to catch it in the act. Number 9. The particles that shouldn't exist. Julian Schwinger spent the years after the war doing unglamorous cleanup work on quantum electrodynamics, trying to make the theory's infinities behave, not searching for anything exotic. The standard picture of a vacuum is simple. It's the lowest energy state possible, defined by the total absence of particles. That's what nothing means. But Schwinger's math said that inside a strong enough electric field, pairs of virtual electrons and positrons, particles that are supposed to be mathematical bookkeeping, not real objects, could borrow enough energy from the vacuum itself to become real, momentarily, before vanishing again. He published the result in 1951. In Physical Review, under the title On-Gauge Invariance and Vacuum Polarization, calculating a threshold field strength of roughly 1.3 times 10 to the 18th volts per meter, the Schwinger limit, above which empty space should start manufacturing particles out of itself. Physicists have spent over 70 years trying to see it happen directly. No lab field comes close. Europe's extreme light infrastructure, built specifically to chase this threshold with the most powerful lasers on Earth, still falls short by orders of magnitude. Proposals to use the magnetic fields around neutron stars as natural laboratories run into a different problem, the distance makes direct confirmation impossible. The effect remains mathematically required and never once witnessed. Every cubic centimeter of space around you and inside you is, on paper, a storm of particles blinking into being faster than any instrument could register, your body sitting inside a churn you were never built to perceive. If virtual particles are real enough to shape outcomes we can measure, in what sense was that space ever actually empty? That one stays theoretical. The next one you can build in a lab. Number 8. The plates that shouldn't move. Hendrik Casimir, working at Philips Research in the Netherlands, wasn't studying the vacuum at all. He was trying to explain why particles suspended in paint behaved oddly, chasing down an industrial question about van der Waals forces between colloids. Classical physics is unambiguous here. Two uncharged, electrically neutral metal plates sitting in a total vacuum should feel nothing between them. No charge, no field, no force. That's what emptiness guarantees. Casimir's calculations said otherwise. The narrow gap between the plates could only support certain wavelengths of quantum fluctuation, while the open space outside supported more, and that imbalance should push the plates together. He published it in 1948 through the Royal Netherlands Academy of Arts and Sciences, under the title On the Attraction Between Two Perfectly Conducting Plates. It sat as a theoretical curiosity for almost 50 years. Then in 1997, Steve Lamoureux at the University of Washington measured it directly, publishing in Physical Review Letters a force matching Casimir's prediction to within 5% at separations under 1 micrometer. Skeptics first proposed residual electrostatic contamination on the plate surfaces, ruled out by controlling for stray charge. Others proposed thermal radiation artifacts, ruled out because the measured force matched the predicted temperature dependence exactly. By 2002, a more precise experiment from Umar Mohideen's group closed the remaining gaps to under 1% deviation. No competing explanation survived. 2 plates on a shelf with nothing between them are pushed together right now by the same nothingness sitting between your eyes and this screen. If empty space can push metal, what else is it doing to matter that no one has thought to measure yet? That's confirmed. In a lab, repeatedly, what comes next has never been confirmed at all. Because the scale is too small for any instrument we've built. Number 7. The foam beneath everything. John Wheeler at Princeton was working through the deep implications of general relativity at the smallest imaginable scales, developing what he called geometrodynamics, trying to fuse gravity with quantum theory into one coherent picture. General relativity treats space-time as a smooth, continuous fabric curved by mass, but well-behaved and predictable no matter how far you zoom in. Wheeler's calculations suggested that assumption breaks completely once you zoom far enough. At the Planck scale, space-time itself should stop being smooth and dissolve into a violently fluctuating structure of shifting geometry, where the distinction between here and there and even before and after becomes unstable. He introduced the idea in his 1955 paper Geons, published in Physical Review, describing fluctuations at the Planck length of 1.6 times 10 to the negative 35th meters, where quantum uncertainty in gravity itself outgrows the structure of space. Physicists proposed testing it by looking for blurring in light arriving from distant gamma-ray bursts, reasoning that a foamy spacetime should scatter light slightly over enormous distances. A 2003 study by Richard Liu and Lloyd Hillman found no such blurring at the sensitivity available, constraining the theory without eliminating it. String theory and loop quantum gravity offer competing, incompatible pictures of what the foam actually looks like, and neither can be tested with any instrument that currently exists. The scale in question is roughly 10 to the 20th times smaller than anything the Large Hadron Collider can probe, somewhere far beneath anything your senses can register. The floor holding your atoms in place may not be solid ground at all, but a boiling, directionless churn. If geometry itself dissolves at a small enough scale, what does it even mean to ask where you are? We can't see the foam. But in 2017, one team caught something even stranger. Space itself acting like glass. Number 6. The light that bent for no reason. Roberto Mignani and his team at Italy's National Institute for Astrophysics were doing routine cataloging work on an isolated neutron star, RxJ8856.53754, measuring basic optical properties, not hunting for exotic vacuum effects. Standard optics is clear on this point. Light passing through true vacuum shouldn't be polarized by the vacuum itself, because polarization requires a physical medium to interact with, and there's no medium in empty space. What they found was light from the neutron star arriving significantly polarized, in a pattern that matched a decades-old theoretical prediction that an intense enough magnetic field can turn the vacuum itself into an optically active medium. They observed it using the European Southern Observatory's Very Large Telescope, publishing the result in 2017 in monthly notices of the Royal Astronomical Society, measuring a polarization degree of about 16% against a magnetic field strength around 10 to the 13th Gauss, a field no facility on Earth can reproduce. Astronomers first proposed the polarization came from the star's atmosphere or surrounding dust, but that explanation fell apart because the pattern matched vacuum birefringence predictions from quantum electrodynamics almost exactly. Alternative theories invoking hidden photon particles remain formally unfalsified, but they require new particles with no other supporting evidence anywhere else in physics. As of this recording, no terrestrial experiment has confirmed the result independently. The vacuum of space is now suspected of acting like a lens, bending and twisting light before it ever reaches your eye, meaning some of what you see in the night sky may already be quietly distorted by nothing. If empty space can behave like glass under the right conditions, how much of what we call empty is actually invisible structure? That's what the vacuum does under extreme conditions. What it does under ordinary ones is stranger still. Number 5. The energy that can't be zero. Max Planck, refining his own 1900 quantum hypothesis, was working through a technical correction to his formula for blackbody radiation, routine cleanup on existing atomic theory, not a search for anything philosophical. Classical mechanics assumed that at absolute zero temperature, all motion in a system should stop completely, a state of total and genuine stillness with no energy left to give. Planck's revised 1911 calculation showed the opposite. Even at absolute zero, oscillators retain a residual energy that can never be removed, a floor beneath which the system cannot fall, present in every field, everywhere, permanently. The result formalized as E equals 1/2 h nu, where his Planck's constant and nu is the oscillator's frequency. And it wasn't just theoretical bookkeeping. Zero-point contributions were directly detected in the specific heat of solid neon by the 1920s. And modern quantum field theory extends the same floor to every field that exists. Some 20th century physicists proposed the zero-point term was simply a mathematical artifact that could be subtracted away for convenience. That trick works fine for everyday calculations. But it collapses the moment the same math is applied to gravity, producing the absurd predictions that later become the cosmological constant problem. No version of quantum theory has ever removed the zero-point term without breaking something else. There is no version of your bedroom at any temperature, in any container, at any point in time, where the space around you contains literally zero energy. Total nothingness is not available anywhere in physics. If energy this fundamental can't be worked around or subtracted away, what does it mean that nothing was never actually nothing? That floor beneath the universe is fixed and unavoidable. What sits on top of it might not be stable at all. Number 4. The mass that shouldn't fit. Giuseppe de Grassi and his colleagues at Rome Sapienza University were doing routine consistency checks after the Higgs boson's 2012 discovery, comparing the newly measured mass against existing standard model predictions, a technical follow-up, not a search for instability. Standard cosmology assumes the vacuum state we currently occupy is the lowest energy. Most stable configuration physics allows the actual ground floor with nothing further down to fall into. Their calculation, using the Higgs boson's precisely measured mass, showed our vacuum sits in a shallow local dip rather than the true lowest point, meaning a lower energy vacuum state exists elsewhere in the theory's landscape. They published it in 2012 in the Journal of High Energy Physics, Higgs Mass and Vacuum Stability in the Standard Model at Menlo, placing the Higgs mass at 125.66 GeV against a stability threshold requiring roughly 129 GeV, landing our universe squarely in what they termed the metastable region. Some physicists proposed measurement uncertainty in the Higgs or top quark mass could shift the result into the safely stable zone. Refined measurements between 2015 and 2018 narrowed that uncertainty and kept the result metastable. Others proposed new physics beyond the standard model, like supersymmetry, could stabilize the vacuum outright. No such particles have turned up in any run of the Large Hadron Collider. The calculation still stands, unresolved. The physical laws governing every atom in your body are currently balanced on a knife edge that, on paper, should eventually tip, not urgently. but with total mathematical certainty built into the same theory that predicts your body's own chemistry. If our vacuum isn't the lowest possible state, what is quietly deciding how long we get to stay in this one? That instability is theoretical. The force accelerating the universe apart from itself is not, and nobody has ever named what it is. Number 3. The push with no source. Saul Perlmutter's supernova cosmology project, alongside Brian Schmidt and Adam Rias's High-Z supernova search team, were independently measuring distant Type 1a supernovae for an entirely conventional purpose, determining how quickly gravity was slowing the universe's expansion down. Standard cosmology in the 1990s predicted the expansion set off by the Big Bang should be decelerating over time, as the gravitational pull of all that mass gradually reins it in. The supernovae came back dimmer, and therefore farther away than any decelerating universe could explain. The expansion was speeding up, not slowing down. Rias and his team published observational evidence from supernovae for an accelerating universe in the Astronomical Journal in 1998. And Perlmutter's team confirmed it independently in the Astrophysical Journal in 1999, together establishing that roughly 68% of the universe's total energy content is this unexplained accelerating force. Physicists proposed it was simply the cosmological constant, Einstein's old fudge factor reintroduced, that fits the data cleanly, but explains nothing about a mechanism. Only supplies a name. Quintessence models proposing a dynamic, evolving energy field were put forward and remain untested to this day. Modified gravity theories designed to eliminate the need for dark energy altogether have consistently failed to match the observational data as well as the simple constant does. 28 years later, nobody knows what it physically is. The space between every galaxy, including the one you live in, is being stretched apart right now by a force with no known source, no known particle, and no known mechanism, acting on you as certainly as gravity does, just in the opposite direction. If 2/3 of the universe is made of something we cannot name, what confidence should we actually have in the third we think we understand? Even that mystery has a measured value. The next one is off by a number too large to picture. Number 2. The worst prediction in physics. Steven Weinberg at the University of Texas was reviewing years of accumulated attempts to reconcile quantum field theory's vacuum energy predictions with what cosmologists actually observed, cataloging a known problem rather than discovering a new one. Quantum field theory predicts the vacuum should carry an energy density calculable directly from the zero-point energy of every field in the Standard Model, a number physicists expected to land somewhere close to what's observed, driving cosmic expansion. When theorists actually summed the contributions, the predicted vacuum energy density came out roughly 10 to the 120th times larger than what's actually measured. Not double, not 1,000-fold, but 120 orders of magnitude off. Weinberg detailed the problem in his 1989 paper, The Cosmological Constant Problem, published in Reviews of Modern Physics. A discrepancy since described by multiple physicists, including Michael Turner at the University of Chicago, as the worst theoretical prediction in the history of the field. Supersymmetry was proposed to cancel the excess by matching boson and fermion contributions against each other. No supersymmetric particles have ever turned up at the Large Hadron Collider to support it. Anthropic reasoning was proposed next, suggesting we only observe a universe with a small vacuum energy because a larger value would have prevented galaxies, stars, and observers from ever forming, which explains why we could be here to see it, not why the number is what it is. No calculation has closed the 120 order of magnitude gap. The same equations that correctly predict the mass of the electron in your body to 11 decimal places fail this specific calculation by more orders of magnitude than there are atoms in every star in the observable universe combined. If our best theory can be off by that many orders of magnitude and still be called our best theory, what does understanding the universe actually mean? Every entry so far describes something the vacuum does. The last one describes something it might do. Once, without warning, everywhere at once. Number 1. The bubble that ends everything. Sidney Coleman, at Harvard, working with Frank DeLucia, was extending earlier technical work on quantum tunneling and field theory, a mathematical follow-up on particle decay processes, not a search for existential risk. Cosmology generally assumes whatever vacuum state the universe currently occupies is either the true lowest energy state, or close enough to it that it will remain stable for the rest of time. Their calculations showed that if our vacuum is metastable, a possibility later reinforced by the Higgs mass results, a bubble of true, lower energy vacuum could nucleate anywhere, at any moment, expanding outward at the speed of light and rewriting the laws of physics in everything it touches. They published gravitational effects on and of vacuum decay in Physical Review D in 1980, calculating that once such a bubble forms, nothing can outrun it, converting all matter it reaches into a different, lower energy configuration on contact. Physicists have proposed that the current age of the universe, roughly 13.8 billion years without any observed decay, sets a probabilistic lower bound on how rare bubble nucleation must be, reassuring, but not a guarantee, since decay is a genuinely random quantum process that could occur at any moment with no warning. Others note that nucleation could already have happened somewhere far outside our observable horizon, expanding toward us at the speed of light, which means we would receive no signal before it arrived. No version of the theory rules this out. If this is correct, there is a non-zero probability that at any second, in any part of the universe, the vacuum itself could fail, with no delay and no possible response before it reached you. How do you live inside a universe whose most tested laws say it could end without warning, and simply hope the number stays small enough to never matter? 10 entries. 10 separate lines of research, decades apart, run by people who weren't looking for any of this. None of them sit at the frontier of speculation. They sit inside the equations we trust the most, the ones that predict your electron's mass to 11 decimal places, and still can't explain the space around it. The universe isn't confused. It's been consistent this whole time. We're the ones still catching up to what empty actually means. If you want to see more videos like this, click the video on screen now.